Hello, pre-calc honor students. Here we are with our last section in limits. Limits involving infinity. Properties of infinite limits. If the limit as x goes to c of fx equals infinity, and the limit as x goes to c of g of x equals L, some constant, then if we add those two together, the infinite limit will take over, and the L is insignificant. If we multiply them, same thing. You're still going to go to infinity, but the sign of L will determine which infinity you go to. And if you look at their ratio, notice if fx is going to infinity, the whole thing is going to approach 0. Okay? Now, we want to look a little more carefully then at rational functions, where the limit of the denominator equals 0. Notice that wasn't covered over here. And the limit of the numerator is some non-zero constant. So notice in each one of these scenarios, the limit as x goes to c of fx equals 0. And notice how fx is underneath every time. Now, division by 0 implies that you're going to approach one of the infinities. So your answer is either positive or negative infinity. It all depends on the sign of the thing you're looking at, both the sign of the upper limit of the constant up on top, and also what values you're passing through as you get close to 0 on the bottom. And basically, it's the same concept of two negatives will make a positive. So in this case, first we can look at this analytically, that we know that if we just plug in and do the plug and chug approach on this, and you get 5 over 3 minus 3, you get 5 over 0. That means we're going to go to infinity, but which one? Well, you can decide by looking at the sign of the top. It's 5 all over some positive number, because as you approach 3 from the left, as you approach 3 from numbers less than 3, you're approaching 0 from the negative directions. So that's why we say negative infinity. So that's how you could do it without ever looking at a graph. I find it helpful to look at a graph so I can see that as I approach 3 from the left, the y values are getting closer to negative infinity. Contrast that now with as we approach 3 from the right, now we're heading up to positive infinity. And so the graph can tell you both those directional limits right away. What would you say then the limit is as x approaches 3 of 5 over x minus 3? What's that going to be? Well, that does not exist because the directional limits do not agree. Directional limits do not agree. Now, technically, the limit doesn't exist here either. But since we can tell what trend it's taking, I want you to say positive infinity if it's definitely going off to positive infinity. Okay, now let's take a look at this one. First, let's do it analytically. You put the 4 in, and you're going to get 2 times 4 over 4 minus 4, 8 over 0. Now, when you divide a non-zero number by 0, that means you're going to get one of your infinities. But which one? Which infinity do you go to? Well, you can look at the signs. Up on top, we're definitely positive 8. On the bottom, you're approaching 4 from numbers less than 4. So like 3.9 minus 4, that's going to be negative. So approaching 0 from the negative, and so that's why we go with negative infinity. Again, the picture can really help you. You get this graph on your calculator, you see there's your vertical asymptote at x equals 4. As you approach 4 from the right, which is what we did here, no, from the left, it's like going this way. Here's 4, and we're approaching from numbers less than 4. We head down to negative infinity. Conversely, if we approach 4 from the right, here's 4 now, we're approaching from numbers bigger than 4, then the y values are heading up toward positive infinity. Remember, a limit is something that the y's are getting closer to. Down here is what the x is getting closer to. So, again, what we call the limit as x approaches 4 of 2x over x minus 4. Well, the directional limits don't agree, so it does not exist. Now, just to review, we did talk about this kind of limit, the limit as x approaches infinity of 2x over x minus 4. Remember we looked at that? Well, it's the first degree over first degree, so you can just look at the ratio of the leading coefficients, so you get 2, and that's where that horizontal asymptote comes into play. And that's true if you approach infinity or negative infinity. Now, limits at infinity, that leads us into our next discussion here. Here's a formal definition of limits at infinity. involving something like an epsilon delta proof, but in this case, for any epsilon greater than 0, that's how we did normally. We don't pick a delta, we pick a number n greater than 0, such that whenever you go past that number, you will get within that limit. Because instead of x getting closer to a number, you can see x's approaches infinity. Okay, so the limit as x goes to infinity of 1 over x, this really speaks out of the graph here. As you approach infinity, as the x's head off to infinity this way, the y's 1 over x is approaching 0. So that's why that limit equals 0. Okay? Now, notice the directional limits on this, just to review. The limit as x goes to 0 of 1 over x, that does not exist. Why? Because the limit as x goes to 0 from the right of 1 over x is positive infinity, and the limit as x goes to 0 from the left of 1 over x is negative infinity. The directional limits don't agree, so the limit does not exist at x equals 0. Now, don't get into the habit, though, of thinking that just because the sign on the infinity is associated with the sign on the number you're approaching. That's just happened in the last few examples. You have to look carefully at the graph and now analyze the thing to see if you're approaching positive or negative infinity. Now let's look at this one. Limit as x goes to infinity of 1 minus x over 1 plus x. Well, this one is nice to look at the graph. We can also look at the ratio of the leading coefficients. Because the degrees are the same, we get negative 1 over 1, which equals negative 1. And that bears out in the graph here. Notice there's our slope of y. Horizontal asymptote of y equals negative 1. Now remember, we used to go through all this. Limit as x goes to infinity of 1 minus x over 1 plus x. You multiply the top and bottom by 1 over x. So you get 1 over x minus 1 over 1 over x plus 1. Limit as x goes to infinity. And then you look at each of these parts here. Limit as x goes to infinity of 1 over x is 0 minus 1 over 0 plus 1, and you get negative 1. So two approaches on that. But if it's a rational function, a ratio of two polynomials, and you know the degree on top is the same as the degree on the bottom, you can look at the ratio of the leading coefficients. Now let's take a look at this one. The limit as x goes to infinity of 3x squared plus 3 over 10x squared minus 3x. Equals 3/10. Because again, we have the ratio of the leading coefficients. So there you go. Now, you can also consider, don't forget the vertical asymptotes. When the denominator equals 0. So 10x squared minus 3x equals 0. X times 10x minus 3 equals 0. So at x equals 0, but also at x equals 3/10. And I want to point out something that often comes up as a mistake when people analyze these on graphs. There's your horizontal asymptote at 3/10. There's your vertical asymptote at 0, and also vertical asymptote at 3.3. Looks like there's a gap in here where the function's undefined. It is defined, though. It's just not showing up on the graph that there is a little downward U in here, way down at like negative 15. So watch out for that. Depends on the window you set up and so forth. You might not be able to see it. Rational functions are defined for all real numbers except where you divide by 0 underneath. Now we're going to look at something called related limits. That is, you look at the limit of the function that it's close to but not exactly equal to. So when you're doing the limit as x goes to 1 of x minus 1 over x squared minus 1, you first try by just doing substitution and you get 0 over 0. That's called our indeterminate form. And you can't stop there and say the limit is indeterminate. If you get 0 over 0, it means it could be anything. It probably means you're going to have to factor something out. In this case, we can. We can say x minus 1 over x minus 1 times x plus 1. We cancel those out. You get the limit as x goes to 1 of 1 over x plus 1. So you get 1 over 1 plus 1 is a half. That's your limit. Okay? Even though at 1 the function is undefined. And these two functions are not the same. If you looked at a graph of y equals x minus 1, let's call it y1 equals x minus 1 over x squared minus 1, and y2 equals 1 over x plus 1, not quite the same. you're going to see that x minus 1 over x squared minus 1 has a hole in it. At 1 itself, the function is undefined. In this case, f of 1 is undefined. The limit as x approaches 1 of f of x is equal to a half. And we express this with an open circle in the graph. At 1 comma a half, put an open circle there. At 0 you went to 1. I'm sorry. There's x squared or x minus 1 over x. Yeah. 1 half. At 0 you go to 1. And it's the graph of 1 over x plus 1 actually. That has a vertical asymptote at -1. But it's got this hole here, and it's got a horizontal asymptote of 0. Horizontal asymptote of y equals 0. And you have this hole in the graph, a hole at 1 comma half. That's called a removable discontinuity, and you'll talk more about removable versus non-removable in calculus next year. Removable discontinuity. It's discontinuous there. It's also discontinuous here, and this vertical asymptote, the vertical asymptote at x equals -1 is a non-removable discontinuity. Discontinuity. Okay? Removable because you could patch this with one single point if you were to redefine the function at that point. This one cannot be patched. To patch it, you'd need an infinitely long line, and that would violate the vertical line test. Here's the second example, x squared minus 9 over x minus 3. We simplify it down to, we factor out the x minus 3, because if you try subbing in right now, 3 squared minus 9 over 3 minus 3, you get 0 over 0. That's the indeterminate form. That means you have not determined the answer. Keep going. Look for some factoring. We factor out the x minus 3's, and now we can evaluate it at 6. But again, this is one of those examples where when you graph it, you get x plus 3. It's a line like that. But at 3 comma 6, you actually have a hole in your graph right there. Limit is x goes to 5, x squared minus x minus 20 over x minus 5. Again, we get 0 over 0 when we try to do it. 25 minus 5 minus 20 over 5 minus 5. When you get 0 over 0, that's a good hint that maybe you should consider factoring. And factoring works well here. Here's again a case where we get 0 over 0. We put 4 in, we get 4 minus 4 over the square root of 4 minus 2. 0 over 0, again indeterminate. So we go back and factor. Now you may not have seen that x minus 4 factors. In fact, we generally think of x minus 4 as something that can factor. So another approach on a problem like this, if you see radicals like this, you can consider multiplying by the conjugate of the denominator, that is the square root of x plus 2 over the square root of x plus 2. And when you do that, the limit as x goes to 4. Don't expand out the top, because we're hoping that this thing will fall out, because that thing's making a 0. We want something that makes it 0 on the bottom as well. So you keep those as they are. Now when you expand out the bottom, you get x, square root of x squared, which is x, minus 2 squared, which is minus 4. See how those cancel now? And now we're all set. Because now you get the limit as x goes to 4 of the square root of x plus 2. And we can evaluate that. Square root of 4 plus 2, 2 and 2 is 4. Okay, flange out.